Now we're going to look at an example using a throttling device, and we want to know the exit temperature of the fluid passing through the throttling device. So let's say that it's a steady flow of ammonia, specifically ammonia vapor, and it's a throttling device, so the picture you should have in your mind is that there's an inlet, an exit, and there's something in between the two that for whatever reason that we don't necessarily need to know, the specific enthalpy is conserved. It doesn't even have to be an object, it can be a physical constriction of the pipe that sometimes works under particular circumstances. Regardless, little h is conserved. That's the defining characteristic of a throttling device. So if we're given that the initial pressure is 16 bar, the initial temperature is 100 degrees C, and that the exit pressure is 4 bar, the exit temperature, well, we don't know, that's what we're trying to calculate. Often this will be the case that a throttling device is used to lower the pressure of a fluid passing through. So if we have this information, we can look in the back of our book to determine the specific enthalpy, knowing that the inlet and exit values must be the same. So if we look at the table for ammonia vapor, pressure of 16 bar, temperature of 100 degrees C, we find that the specific enthalpy at the inlet is 1644.56 kilojoules per kilogram. It has to be the same at the exit because this is a throttling device. Now, we can go and try and look up that exact value at a pressure of 4 bar to see what the corresponding temperature is, but you can imagine that the table probably won't contain that. So what we can do, if we look at the table according to 4 bars for ammonia vapor, we see that at the exit pressure, there is a table entry at a temperature of 100 degrees C, so I'll label that H100. And again, this is at 4 bars now, which is why it doesn't match up with the value over there on the left for H sub I. Likewise, there's another entry in that same table at 80 degrees for the same pressure, so H sub 80 is this other number. We know that we're looking for a specific enthalpy of 1644.56, and I picked these two values because they're the two nearest values on either side of it. So this seems like a good candidate for an interpolation problem. If we know the specific enthalpy at a temperature of 100 C, we know the specific enthalpy at 80 C, we can actually figure out what the temperature must be, knowing that we want a target specific enthalpy of 1644.56. Let me walk you through the interpolation just to make sure everybody's okay with this. Okay, so the ratio that we're going to set up. Well, we know that the difference in specific enthalpies at 180 degrees C divided by that temperature difference should be the difference between the actual exit specific enthalpy that we have, H sub E, and the value at 80 degrees for 4 bars, divided by that temperature difference. So we can solve for T sub E just using the simple ratio that is an interpolation ratio. We do that, and we find that T minus 80 is all that stuff on the right, and now we can just solve for T sub E. Okay, great. So we have a formula for T sub E, and we have all of those values. Remember, the exit specific enthalpy we got from knowing that it had to be the same as the inlet specific enthalpy. H80 and H100 we just looked up in the table, knowing that we had to have ammonia at a pressure of 4 bars, and we picked the nearest values, making sure that if we did that, the linear interpolation would be as good as it gets. Okay, so let's plug in some values, and we do that. We'll simplify this a little bit. Alright, we get that, and our final value for the exit temperature is 83.5 degrees C. As a sanity check, we can look and see, well, we were interpolating between temperatures of 80 degrees and 100 degrees, and we are between the two. That's good. It's also the case that H80 is a little bit closer in value to HE than H100 is, so we would expect a temperature a little bit closer to 80 degrees than to 100, and that's what we got. This problem also indirectly illustrates something interesting about the listings in the back of our book in the NIST website. So I'm going to record our temperature of 83.5 degrees C over there as found from using our book. If you try doing the same problem with the NIST website, you'll actually get about the same answer, but with different numbers, which is a little weird. A few students asked me about differences between the NIST website and the back of the book. This is one that I wasn't aware of, but discovered, namely that it doesn't always list the same values of the specific enthalpy. The nice thing is, though, it does list corresponding differences correctly. So what they're probably doing is using a different 0 point for the internal energy. There are complicated details having to do with that choice, but for our purposes, the important thing is that you get the same answer when you do the same problem. I'm going to go through and do this using the NIST website. So what I'm going to do is erase all of that and the information we had about the exit pressures. Let's say that we had instead looked up the inlet specific enthalpy using the NIST website. So on NIST we looked up 16 bar and 100 degrees C with ammonia. We would have found that actually the inlet and exit values for a throttling device had to be 1807 instead of 1644. So I'm going to replace those with 1807. Let's see what happens when we use the NIST website now to solve our problem. You have to use the same device. You don't want to jump between the book and the NIST website if they use a different 0 point, but as long as you're using the NIST website for the whole problem, or your book for the whole problem, you should be fine. Let's go in and see how we would do this with the website. So I'm going to fire up my device. Here's the NIST website, and let's go. Now remember, the goal here is that we want to look up ammonia at a pressure of 4 bar, scan through until we find the temperature that corresponds to a specific enthalpy of about 1807 kilojoules per kilogram. Okay, so let's do that. And we'll pick ammonia here. So we scroll down, eventually find ammonia. And we want to work in the right units. Let's pick Celsius bar, kilograms per cubic meter, and kilojoules per kilogram. Fine. Let's pick isobaric properties because we know that we want 4 bar. Okay, so we'll enter in 4 bar up here. Now, the pressure is fine. We know what that has to be. The temperature range we have to guess, let's guess a wide range, going from something like 50 to 100 degrees C, with the smallest interval we can, just so we have a lot of data to scan through to find that specific enthalpy we wanted. And let's look in a table. All right, so the enthalpy column is going to be right up here, and it's in the correct units. So remember, we're scanning through and we're looking for 1807. So if we find something close to 1807, we should be able to look to the left and find the corresponding temperature. All right, scroll, 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 scroll. This takes a little while. And we're getting closer. Now we look and we have 1807. Okay. So look over, and it's 83.4 degrees C, so that's the corresponding entry for 1807 kilojoules per kilogram. Well, that tells us that that's about the same answer. So to better than a percent, we get the same answer, even though we listed the specific enthalpies different on the NIST website as in our book. It turns out that the only thing that matters is the difference, and in this case, the difference was 0. You get the same answer either way.